Hey everybody, we're going to be talking about some circulations that are associated in tropical meteorology. One of them we've talked about before in dealing with the El Nino, and that is the Walker cell. The Walker cell is an east to west circulation. Primary manifestation is going to be over the Pacific. But we also have a north-south circulation known as the Hadley cell, which we'll also want to talk about. So in order to do this, let's get to the blackboard. And the first thing we'll do is we'll share the screen here. And I think we can move me up to the side. Let's go to here. So if you recall from class, we did say here's the ocean, here's the Andes of South America, and here's Australia over here. And basically what we're saying is that this circulation is a result of higher pressure near the water over near South America and lower pressure over here. So there's an L for low, H for the high, and we are saying that the circulation is basically going to come across the ocean this way, where it's going to rise up, it's going to come on higher in the atmosphere, back to the east, and then it's going to come down. And the key thing here to remember is that circulations, or in other words, winds, are firstly, so I'm going to even write that word down, firstly, a result of a pressure gradient. Okay? So we have higher pressure here, lower pressure there. This is a pressure difference over a distance. That's what a gradient is. We've talked about this before. This should be something that's fairly clear to you. So the air, generally speaking, wants to go from this region of higher pressure to the lower pressure. So this is what we call the Walker cell, which is east to west, or we call that zonal. So the term is zonal, which is east to west. Okay, that's just an important word that we use in meteorology. To anything that's going west to east, east to west, that from one longitude to another longitude, that's going to be known as a zonal circulation. But it says it's firstly a result of pressure gradients. Secondarily, they are a result of a temperature gradient. So first thing, they're a pressure gradient. Second thing, they're a temperature gradient. So what we mean is that we've got cold air over here where the waters are relatively cold and warm air or warm water over here. Now, this is where we're saying that we have warm air rising, and there's going to be thunderstorms over here, and that is like a thunderstorm, warm air rising. But over here, it's going to be cool air sinking. And when we get into the next lecture, we're going to be talking about thermally direct circulations. But I want you to know that this is what we're going to call a thermally direct circulation. The warm air, or the warm branch of this circulation, is where the air is rising and the cold air sinking. So this circulation, the basic speed of it is a result of the difference in the temperatures from there to there. The bigger the difference in temperature, the stronger the circulation. So we said in an El Nino, the Walker cell weakens. Well, why is that? And the reason for that is that this area here in an El Nino, the El Nino 3.4, is going to be warmer than normal. It's an anomaly above normal, which means that the zonal temperature gradient is less intense. I want you to write that down. Because the water here in the Pacific is warmer than normal, the zonal temperature gradient, the east-west temperature gradient, is less than normal, and that will cause this circulation cell to weaken. Typically speaking, we are going to say that the water near the Australian, Indonesia, Papua New Guinea, that area is always going to be warm. It's this water here in the El Nino region 3.4, 3.4 is going to be warmer than normal, which means that the difference is less. The gradient is less. And that means this circulation weakens. Okay? So the Walker cell zone east-west, the warm branch rises, cool air sinking, that's thermally direct. And we understand that in an El Nino, this should be weaker. Now, in a La Nina, this is colder than normal. This water over in this region is colder than normal, which means the zonal gradient is bigger than normal. It means the winds are going to be stronger. So that's what's going on zonally, east-west. However, on the globe, and I'm going to go ahead and erase this and show you a picture here because I did get one ready. This picture shows you what all the winds are on the planet, generally speaking, okay? So I'm going to go ahead and erase all this, and I'm going to have my pen out, and I'm going to say, notice in the tropics, we've got rising air here, and it's warm by the equator, and then when it's slightly cooler, the air is sinking over there. So we still have a thermally direct circulation, but notice this is a north-south circulation. So it's low pressure here, and I'll draw it so that it's right side up in a little bit, and it's higher pressure here in what we call the horse latitudes, low pressure near the equator. Well, it's warm air rising, cold air sinking, and we get thunderstorms that kind of form over here. Well, this region is called the IT, oh, that's a C, the ITCZ, which stands for the Intertropical Convergence Zone. And the air is coming together in this region here. They're going to draw it. I'm going to talk about that, but they're coming together slightly over here. So the air is converging. Mass continuity says it's going to rise, and then it sinks over here at 30 degrees. So just so you know, this area usually is fairly dry because of the sinking air, and this is where the deserts of the world are. If you take a look at the planet, the main big deserts, the dry, hot areas are going to be around 30 degrees north latitude, even 30 degrees south latitude. Sahara deserts in there, the Gobi Desert, the desert southwest, the Great Australian deserts down here in the south. So we have this circulation that kind of goes this way. Well, this circulation is called the Hadley cell. The Hadley cell. Let me write that neat, I think. H-A-D-L-E-Y. The Hadley cell. And if you want to be precise, this is actually the tropical Hadley cell, because it's in the tropics. Over here, there's another cell called the Ferrel cell. Over here, there's a polar cell. In some other classes, we talk about those circulation cells, but this is the one I want to focus on here. This is the Hadley cell. And the Hadley cell's got the warm air rising at the ITCZ, and this is where you've got lots of thunderstorms. These thunderstorms over there are called hot towers. And the reason they're called hot towers is they release latent heat very high up in the atmosphere, way high up. Now, because I've got this circulation, do you agree that it is north and south circulation? So the Hadley cell is what we call a meridional circulation, which means it is north and south. Okay, so if I were to go over here just for a second, I'm going to do this so that I can look at it this direction. I want to think of this as the equator here, and I'll go 30 degrees south latitude and 30 degrees north latitude. And basically what I'm saying is I've got air that's rising here. It's going to diverge. It's going to sink at 30 degrees subsidence and come over this way, and it's reflective this way. Now, this Hadley cell is super important when we start discussing hurricanes, so I want to make sure that we have a good idea of conceptually what this is. Over here, this is the ITCZ, and if you look at the hurricane notes, you'll see a definition in the notes of what the ITCZ actually is. We say it's at the equator. Really, it's a little bit different. It changes its location. It's got some variability, in other words. But generally speaking, this is what's going on. Now, given this scenario, what that says is I've got an area of high pressure there and an area of low pressure here at the ITCZ. So I still have warm air rising, cooler air sinking, thermally direct. We're going to talk about what that does, but it's warm air rising, cold air sinking. But again, the reason for this Hadley cell is that it is a difference in the pressure. Well, what do we say? That's the primary reason, or actually the one that we said is first. The second one is a result of a temperature difference. So we're talking about the temperature difference, especially in the water temperatures, from higher latitudes to the equator. And the reality is this is typically warmer. And this, even though it's not a huge difference, is slightly cooler. So I have going from the high pressure of cooler air, bringing to the warm air here. Okay, now with that in mind, let's go to this picture here. So what I want to do, and I'm going to go ahead and erase this, is I want to say this is where I've got high pressure, and this is where I have low pressure. Okay? But in an El Nino, if I think of this as being the El Nino region 3.4 in here, this water in an El Nino is hotter, it's warmer than normal, which means my meridional temperature gradient from 30 degrees latitude to 0 degrees latitude, that north-south temperature gradient is going to be bigger. The bigger that gradient, the stronger that circulation. So during an El Nino, the Walker cell weakens, but the Hadley cell strengthens. Now, super important that you get these right. El Nino, Walker cell weakens, Hadley cell strengthens. The other way around, in a La Nina, this water is colder than normal. This water is colder than normal, which means the meridional gradient in temperature is less intense. As a result, the Hadley cell is weaker when the Walker cell is stronger. So they go back both ways. Now, I want you to notice something here, that it says they're the northeast trade winds, and in the southern hemisphere, they're the southeast trade winds. So I'm going to go back to this, erase this, and I'm going to look at this region, just one place, from around the equator, so the equator there, to maybe 30 degrees of latitude. And we said the winds are northeast trade winds. By the way, trade means persistent, sort of blowing all the time. And they're really, for the most time, they're going to be somewhat out of the northeast. So let's just say we go there and we got a northeast wind, right? We have a northeast wind. Now, what does that mean? Well, it means that we can break it up into components. We've done this before. We can say we have a north-south wind, and then we have an east to west wind. So that the red plus the green is equal to the blue. We have broken things up into components, very similar to what we do when we're dealing with radar. So do you understand that when I've got these persistent winds that are out of the northeast, there's a component that's out of the north? Well, what is that component out of the north trying to represent? It's trying to represent the Hadley cell. And I'm going to say the Hadley cell component. Okay? What's the green? That's a zonal wind. So that is the Walker cell component. Okay? So let's go back to an arrow here representing the winds. During an El Nino, the Walker cell weakens and the Hadley cell strengthens. And in other words, the wind becomes more like this. Does that make sense? So if you look, think about the green arrow becoming smaller and the red arrow becoming larger. So that means the wind becomes more northerly. Southern hemisphere would be the same, which means during an El Nino, with the Walker cell weakening and the Hadley cell strengthening, I get more convergence in the Pacific. In the middle of the Pacific, where I get those thunderstorms really going crazy. So I get an active central Pacific. Nobody's really living there. I mean, there's islands and everything, but the big continent, or Indonesia and Australia, that area where all the people live, that's not where the thunderstorms are happening, because there's more convergence, and therefore we would say there's more storms in this region. Okay? Now, what happens if I go back over here and I say, well, what if we had a time where it was a La Nina? In that case, the Walker cell, or the green, becomes stronger and the Hadley cell becomes weaker. So the winds are going to be more like this. And the southern hemisphere, instead of being this way, it's going to be more like this. Do you see now that the convergence is less? So I don't get those thunderstorms forming in the Pacific. There's less convergence along that. So when we've got a circulation, I really want you to think of this as being, here's your typical, or what we call an enso neutral. It becomes more like this during an El Nino, and it becomes more like this during a La Nina. So do you see that this wind goes back and forth? It goes back and forth, and if that's the case, going back and forth, we get an oscillation. And that's part of the El Nino southern oscillation cycle. We get variability within the atmosphere. That's going to be kind of important, because if in the Pacific, and so now you're going to have, here's Alaska, here's California, here's the Baja Peninsula, here's into Mexico, here's South America, Central America, something like this. So if you think of this as the West Coast, then if I've got more storms, which certainly warms the atmosphere, the jet stream is going to be pushed further to the north. And then you get more action by the time it comes into the west coast of the United States, maybe into California. During an El Nino, we tend to get more weather systems coming into the west. That's what's going on. If I get less storms, so I can go here and say, if I have less storms, then I don't get the jet stream being as pushed to the north. I'm not getting that heat going to feed the jet stream. And so the flow comes over this way and it kind of goes up this way, and I get less storms. So La Nina, we'd expect California to be less in terms of precipitation. Generally speaking, now this is something that in the notes it talks about that this is not always the case. In the Pacific, there's a lot of events that happen close by that's well correlated. Because of the El Nino, there's dryness in Australia, or there's more thunderstorms in the Pacific. But because of the El Nino, how it affects our weather here in Chicago, it's a little bit more uncertain. So we don't do a very good job forecasting the El Nino, and I can give you some fantastic examples of complete failures. But that's what's going on. Now, the last thing that I want to talk about is I'll go back to this thing. So here's the water again. Here's the Andes. Here's Australia. And we're looking at an El Nino. Well, if I said that in El Nino we have more thunderstorms than normal, is there a way that we can look at this? Okay, now I want you to imagine that this is a satellite looking from space. So here's a satellite. I don't know what a satellite looks like. It's got some wings on it. I don't know what this is. That's a satellite, just pretend. Okay, and it's gonna look at infrared. So it's gonna be infrared, IR satellite. And that satellite is measuring temperature. Now, normally, if there's no thunderstorms, what is it measuring? It's measuring outgoing long wave radiation. It's called OLR, which stands for outgoing long wave, which I think we've talked about, radiation. Well, if the satellite's seeing the water, this is warm. The waters are relatively warm, it's near the surface, and it's going to be that much, some amount of outgoing long wave radiation. But if it's coming from the cloud top, where it's much colder at the top of a thunderstorm, it sees less OLR than if there had been no thunderstorms. So if there's less than normal radiation that the satellite measures, probably is because there's a thunderstorm in the way. Rather than seeing radiation coming from the warmer waters, it's seeing radiation coming from the cooler tops. So we say that there is a negative anomaly in OLR. Negative anomaly in OLR. And that means more T-storms than normal. Rainier, thunderstorm, more thunderstorms, more rain. It's less infrared radiation coming out because I'm seeing the top of a thunderstorm rather than down below. Excuse me, down below. Okay, now let me show you an example of that. So I'm going to go over here to our website and I'm going to look at something over here, climate. And we've already taken a look at some of these with SSTs, but now we have an outgoing long wave radiation. And if I look at them in this sector over here, the warmer temperatures are positive anomalies. And if it's positive anomalies, it means there's not as much rain as normal. So over here, what this is saying, and it's brown because it's drier than normal. If it's green, it's wetter than normal. So I've got, over the last day, I've got some precipitation that's going on here. It's telling me basically where there's thunderstorms. Now, it might be better if instead of looking at maybe the last day, I'm going to go back down and maybe look at the last month. Okay? I'm having a hard time getting to this, so I'll go over here. And for the last month, we are seeing definitely drier than normal conditions throughout the Pacific, which is what we'd expect because right now, what are we in? What are we in right now? I'm going to go ahead and give you our sea surface temperature anomalies for that same region. And sure enough, we're in a La Nina. We don't expect there to be thunderstorms. So we use OLR to kind of judge, well, are we getting more rain than normal? And I can certainly do that. Like right now, it's December 7th of the year 2020 when I did this video. And if I look at maybe over here, maybe if I look at the Gulf of Mexico, or maybe it might even be better if I just look at the world so you can see the US. The US is going to be drier than normal conditions, a little bit warmer than normal, and that's what's been going on because we're starting to build a drought. We're in a La Nina. We do not expect thunderstorms to be coming into California, and so it's drier than normal. Where has it been rainier than normal? Well, over the last 7 days, maybe a little bit down here. It's been wetter than normal. Maybe a little bit over there, it's been wetter than normal. And if I even look at this in terms of maybe 30-day anomalies, I'm seeing the United States is fairly dry for the last 30 days, which those of you who can remember this, it's been fairly dry. The only difference is it's been wet here way to the south, and at the end of 2020 we had a number of hurricanes. There was a big hurricane that came in and affected Central America. So that shows up on the anomalies of the OLR as well. So this is how we use satellite to tell us something about the long-term weather impacts. That we're getting anomalies that are warmer than normal, and they indicate that it's drier than normal. Okay, so with that, I'll stop the screen share and say that is a really important lecture. It's a pretty advanced one, but take good notes on that, and there'll be test questions that'll come right off of that note. Okay, see you guys later.